Hi, everybody. Welcome back to the Feynman technique. Here's an integral I got off the channel Maths 505. The process for solving it is going to be slightly different than the process he used. I will be using Feynman integration. He did also. Um, I'm going to take my path is going to be a little bit different than his. Um, the main difference is we will be taking for granted this fact that the integral from negative infinity to infinity of cosine of x squared dx is equal to the square root of pi over 2. Not the square root of pi divided by 2, the square root of pi over 2. So we will be taking that for granted. Okay, so let's go ahead and get rid of this. And let's continue with the integral. Second. Okay. So the first thing I want to do is I want to set it equal basically to itself, except we're going to bring x to 1, to 1 over x. And what I mean is we're going to be making the substitution u is equal to 1 over x, and then replacing our dummy variable u back with x. We're going to put x right back into it. And if you want to do that yourself, go ahead. But what you'll end up with is this, the integral from 0 to infinity of sine 2 natural log squared x over x times x plus 1 times natural log squared x. So it's almost the same thing. These two integrals have the same value with the substitution u is equal to 1 over x. Okay. Now what I'd like to do is take our original version of our integral and just multiply the top and the bottom by x. All right, now we have the same denominator in each one of these integrals, so we can just add these things up. In other words, we'll have 2I is equal to the integral. Yeah, we have the same bounds of integration too. That's a necessary step, necessary condition. And then let's see, we just add the numerators together and put them over the denominator. Well, let's see. We have a factor of x in front of our sine in front of our sine of 2 natural log squared x, and in this version we have a factor of 1. So that's going to give us a total factor of x plus 1 times sine of 2 natural log squared x over x times x plus 1 natural log squared x dx. And you can see that x plus 1 cancels nicely. All right, so this implies that I is equal to 1/2 of the integral from negative infinity to infinity of sine 2 natural log squared x over x natural log squared x dx. And now I would like to make the substitution that u is equal to natural log x. Implies du equals 1 over x dx. And you can see we conveniently have a 1 over x dx in our original integral. So this means that our integral is now 1/2 the integral from, I'm sorry, this is not a negative infinity. I don't know why I did that. That's a 0. Natural log, so now our u goes from natural log of 0, which is negative infinity. Jumped the gun a little bit there. To infinity of sine of 2u squared over, let's see, u squared, and then we have our 1 over x dx, which is equal to du. All right, so now what to do? I think now is the time to reparameterize our integral. Let's create a function of t equal to 1/2 the integral from negative infinity to infinity of, you guessed it, sine of t u squared over u squared du, noting that f of 0 is equal to 0 and f of 2 is equal to our original integral. All right, so this is not going to be the actual substitution that I'm using, but it's the motivation for the substitution. I would like tu squared to equal some other variable just squared. Now, this is not technically the substitution that we're going to be using, because you would see that this would actually change our bounds from I believe, infinity to infinity. Because if we let u equal negative infinity, we'll get infinity, which means that our lower bound would also be infinity. This is just the motivation for our substitution, because I would like there to just be a, well, actually, I jumped the gun again. Let's go ahead and take a derivative with respect to t of our f of t using the Leibniz rule for differentiation under the integral sign, which says that we can take the derivative with respect to t of this f of t by taking the integrand and taking the partial with respect to t and leaving the rest alone. In other words, our f prime of t is going to be equal to 1/2 the integral from negative infinity to infinity of the partial with respect to t of our integrand. That's just going to give us cosine of tu squared du. Because if we take the derivative with respect to t of the inner function, we recover a u squared, which cancels this. That was the whole motivation for our reparameterization there. Okay, now I would like to have some w squared equal to tu squared. And like I said, this can't really be our substitution as it's written, because then we'd end up with bounds infinity to infinity, and that wouldn't be any good. All right, but let's just take the square root on both sides. So let's just say that w is equal to t to the 1/2 u. It amounts to the same thing. We'll still end up with a w squared in there. Okay, so this implies that our du is equal to t to the negative 1/2 dw. Okay, so now our f prime of t becomes, well, let's see, we're still going to have our 1/2, and we'll still have the integral going from negative infinity to infinity, since our new variable is just a constant multiple of our old one. And then we will have cosine of w squared. That was the whole point of the substitution, was to get that. And then our du is t to the negative 1/2 dw. All right. And now you'll remember from the beginning of the video, I said that integral right here, that whole thing is just the square root of pi over 2. So this whole thing is equal to, That's going to give us all and all. That's going to give us the square root of 2 pi over 4 times t to the negative 1. Yeah. Square root of pi over 2 is square root of 2 pi over 2, and then times 1/2 is square root of 2 pi all over 4, and then times t to the negative 1/2. So there's our f prime of t. Well, we have f prime of t, so let's find f of t by integrating f prime of t. This is the integral of f prime of t, which is the, let's see, that's the square root of 2 pi over 4 times the indefinite integral of t to the negative 1/2 dt. I'll put a dt here. Which is equal to, let's see, square root of 2 pi over 2 t to the 1 plus c. Don't forget, we did an indefinite integral, so we have to have a constant of integration. All right. Well, we know from up here that f when t is equal to 0 is equal to 0. So I'll just write this down. F of 0 is equal to 0, but it's also equal to this thing evaluated at the point 0, which means that it's equal to 0 plus c, which implies that c is equal to 0, which implies that our final version of f of t is simply equal to the square root of 2 pi over 2 times t to the 1/2. And now all we have to do is plug in 2 for t, and we have the value of our integral. So the value of our integral, I, is equal to f of t, f of 2, which is the square root of 2 pi all divided by 2 times 2 to the 1/2, which is just the square root of 2. You'll see that this square root of 2 times this square root of 2 will be a 2, which will cancel that 2. So this is simply the square root of pi. So that's kind of neat. That's this is exactly the value of the full Gaussian integral. All right, guys. There you go. I hope you enjoyed that. I thought that was a pretty cool integral. Credit to Maths 505. I will try to remember to link to his video in the description of this one if you want to check that out. But until then, we will see you next time.